There we go. We are now recording, and also let me record WebEx. Oh, you know what? I had this muted, so if anybody ever talked right now, I did not hear you guys. Until I highly doubt anybody did, but I had the computer muted. Let me see if there's audio now. Okay, there's audio now. So apologies if anybody said something I didn't hear you. So yeah, okay. So today we are going to pick off where we left off last time with Big O. Before that, I would like to notify you on the results of the poll. So we had a 75% of you voted to do Twitch and 25% of you voted to do WebEx. So we are going to be moving to Twitch starting next week. But we have Labor Day off on Labor Day on Monday, so we don't have class on Monday. So we will be moving over there on Wednesday. So a week from next Wednesday. That's September 8th. I sent out a couple of messages. First, we were going to go on Monday. On Wednesday of this week, but I delayed it by one day. So now we're basically going on the Wednesday because of the holiday. Okay, so you have basically about 10 days to essentially get Twitch, you know, an account on Twitch, which is free, so that you can write comments and whatnot. And we will be doing probably the points, attendance points for extra credit. So if the channel points they're called. So if you want to get extra credit, you can just have it open, I guess, even if you're not watching. But I would encourage you to watch live, because then you can actually stop me and ask questions. So, which is better than sending me a message later on and then having to wait for me to respond and whatnot. So, yeah. Okay. So that is going to be happening. So we will have class Wednesday on WebEx. Okay. But the week after, so that is September 8th. Just check your messages. That will tell you everything. Okay. And I will send out reminders later on over the weekend and whatnot. How do you get channel points just to be there? Yes, as long as you're logged in to the account and you're watching the stream, then in theory you get points. They slowly get points. I don't know, you know, people actually like for like other things on Twitch, they get points to do things like buy things or whatever. So like people have tried to sync convert the system. And there's things to avoid that. So I think that you have to be actively there. I don't know how they check that. I don't know if they're checking like if there's mouse movement or something, because there's limitations what you can do from the web browser. But at the very least, you have to have the stream open. I know that much, because I know when the Valorant key drop came out years ago, people were trying to do that, and like I think they were saying like, oh, you have to at least write a message once in a while so it knows you're active. So I don't know. So my tip to you for that is be there. And occasionally say something on chat, maybe. Okay? Kind of what you would do here. So, yeah. Okay. So let us go ahead and pop open the iPad. Oh, I forgot I closed this. Let me just reopen it again. There we go. Okay. So welcome all again. And let me go ahead and just move this over here. So this looks like 202, not the right class. Okay, 302. Here we go. Space and time. That looks more like us. Okay. So let's go ahead and kind of review what we did last time, just to refresh in your mind over the long weekend. So we talked about what an abstract data type is, which is ADT, and that's basically a set of values and operations. And we talked about that basically if we want to implement this into like actual code, that's what a data structure is. And the things that we're interested in when creating a data structure are inserting data, retrieving that data, and deleting that data. And in addition to that, we want to be able to modify and process the data, but that's really just a combination of these three things initially there. Okay, an example of that is a linked list, storing data into a linked list, being able to access that data, which is the retrieval process, and being able to delete the data, which is a mixture of both retrieval and delete if you're trying to delete a specific item in the data, or if you just want to delete everything, right? So even retrieval is even deletion is kind of requiring retrieval, because otherwise you're just deleting things randomly. But ultimately, those are the main things that you want to have in a data structure, and you optimize for one of them. You typically want to have everything be super fast, but you have to pick which one you want. You want fast insertion, fast deletion, or fast retrieval. So with that, we kind of segue into talking about space and time. So space and time. Time is going to be how long a program takes to run. One way of measuring that is in seconds or clock cycles in a computer. But the issue with these things is that different computers have different amount of capabilities of running something. So they have a faster frequency, so they can process information faster, or they can just, they have a better processor that just flat out doesn't necessarily mean that it has a higher frequency, but that it can still do more instructions per second. So those are not good measuring points for us. So because we want to be able to compare an algorithm regardless of the machine that you're running into. You want to abstract that information. And so ultimately what we decided to say is we're going to count it based on the number of operations required. So for example, if you're sorting something, the number of comparisons that you need to do, the number of swaps that you need to do, those are things that are easy to measure. And then yes, you can figure out how long a swap takes in your personal computer, but that doesn't matter because again, we're just trying to see the general overview of like the meta of something, right? So that's when we talk about time. When we talk about space, that has to do with storage. So how much space, like as in storage, how many bytes, how much RAM do we need to be able to store information, right? And in the past, these two things were, I would say, is equally important when computers were starting out. Nowadays, space is very cheap. We're in the terabyte age, at least for personal computers, and for servers and things like that, I think they're in the exabyte age at this point. So it goes terabyte, petabyte, and then exabyte. So I think that's where we're at. Like Google and whatnot have like 160 exabytes or something. I might be throwing those numbers off, but the point is that we got tons of space, and space has become very, very cheap. It's not super cheap, but it's cheap enough that like you can go and buy a 1 terabyte hard drive for less than $50 probably. I would say. I think. I mean, I don't know, pre-pandemic at least. I don't know like prices and whatnot, right? But like that's how cheap space has come. Now, of course, comes the time. Time is not something that we can make cheap, right? We have a limited lifespan ourselves in a way. So ultimately, when it comes to a computer, the faster the better. Like we want things to be instant, and even then, they might not be fast enough, right? So even with storage, we go into that sort of world because we have things like a solid state drive versus a hard drive, right? And you will talk about this in 219, but ultimately the solid state drive has faster retrieval, insertion, and deletion. Well, deletion, I don't know. Deletion might be the same between both of them because you're really just marking something for deletion, but definitely for retrieval, it will be much faster, right? So even within storage methods, time becomes a big necessity, right? And that's what makes an SSD more expensive than a hard drive, but still more desirable. So ultimately, I would say that because of that, it also affects this class in the sense that we care more about time than space. But I do want you to be aware that space is one of the two major things. It's just that like nobody cares about it anymore. We're all about space these days. Sorry, we're all about time these days, okay? So that's pretty much the main things that we talked about. I've actually watched a video on a petabyte server build. Yeah, I mean, Google has like ridiculous amounts of data every week. Facebook, Google, the big companies like that, they have. I used to know these numbers when I taught 219, but hey, we'll watch my YouTube lectures on 219 and you'll probably find that information there. But yeah, they big data is big. Like nowadays, it's real big. Big data is not terabyte size. No, that's nothing. That's like nothing. So I mean, yeah. So anyways, from there we segue into saying we know how we're going to measure time. We're going to measure in operations. Now, how do we actually write this down? How do we make it into some mathematical thing that we can compare so that I can say my algorithm is faster than your algorithm, and they can both achieve the same thing, which makes mine more desirable, right? I can make the big bucks selling it or whatever. And so that's where asymptotic complexity comes into play. We said that we created these lines that represent the operations over time. So in fact, I think the other one of these I labeled. Yeah, this one I labeled. So we had operations, and then we had n as in time, right? So sorry, the n is the number of data that we're working with, and the operations is how long it takes for that. Okay, so you can think of this as your time. There we go. You can think of this as time increases, and then this is like number of data to process. the most simple example for you to picture this is sorting, okay? The bigger the number of items that you have to sort, so if you're trying to sort 100 numbers, that's n equals 100. If you're trying to sort 1,000 numbers, n equals 1,000, okay? And then operations is how many swaps and how many comparisons you have to do, okay? For now, let's just think about comparisons. Don't think about swaps, for at least for sorting, okay? So that means you have to look at two numbers and decide which one is bigger than the other one or something, okay? That's going to depend on the algorithm. But that's what I mean by number of operations, okay? So obviously, the more operations something takes, the longer it's going to take. That's why we associate that with time. And then with data being the n, okay? So all of these graphs have the same labels. I just didn't put them, okay? So we said, okay, we have this line, and this is a linear growth, and we have 1/2 x, right? And we remember our math, mx plus b, where m is the slope of a graph, which is how steep it is, and b is that y-intercept, which is like this or that shift up or down, which never going to go down. It's always going to go up. But yeah, it's all going to be positive. There should never be a negative x, but never say never. I don't know. There might be some algorithm that like, yeah, okay, yeah, maybe, okay. You never know, right? Otherwise, you can come up with one probably and like be my counterexample. So anyways, what we did with this is we said, okay, we have line, when the line is straight like this one, we can just like figure out that line and we're good to go, right? We can say, okay, well, you know, we can put a line on top of it and we can put a line beneath it and sort of contain the duration of an algorithm, right? And that one is going to be this one. So we said, okay, this line right here, let me highlight it with another color. This line represents the actual time the algorithm takes, okay? Now, trying to actually come up with a graph or a formula, like a math formula to actually draw that line, like practically draw that line, is very, very complicated, right? Because it's experimental data. So what we want to do is we want to mathematically come up with approximations that either under approximate or over approximate that expected behavior. And so that's what the orange and red lines are. The orange ones on the top, the red ones on the bottom. So basically we say, okay, that line looks like it's a quadratic. So it's a parabola, right? And so if we do 1/2 x, which is the orange line, we guarantee that that line will never touch the green line, but it will always be above it. Now, what does that mean to you? What does it mean for a line to be above it? So we have two lines. So we have the remember the Jane and Joe example, and I asked you which one's more efficient, right? And you said Jane's is more efficient because it's lower, right? It's less operations even though you have more data. And you're correct. Jane is more efficient in this scenario. Then we also gave you the counterexample here where like if we zoom out, we can see that they're actually both, Jane's is actually a parabola that just kind of grew really slowly. So this was fooling us, whereas this one actually showed the real picture, right? Which is why just graphing these things is not ideal. You actually want to mathematically get a formula because then the formula will prove to you that regardless of what n is equal to, you're still going to be within those parameters, right? And so that's how we kind of came up to this and we said, okay, well, mathematically, and again, I haven't told you how to do that yet. That's not easy. Figuring out what these lines are is not as easy as it looks. But anyways, once you go ahead and figure out and say, okay, 1/2 x squared is going to always be above that line, then that's what we're going to call our big O. And our big O is going to be our upper bound of the growth of this. So what we're saying is that no matter how far we go, you know, if how far we like zoom out, so we can go to like n is equal to a trillion or something, we are guaranteeing that the orange line is always going to be above the green line, okay? On the other hand, we look at the bottom, so the lower bound, okay? So let me put those words in there because they're kind of important. The big O is upper bound. I don't know if big O is like big OH, but I've seen it both ways. I've seen like people write big O just like that, and I've seen people write big O like that. So yeah, I go on back and forth, okay? And then this one's going to be your lower bound. So this is your omega, like think omega low, okay? So that's your lower bound, all right? And then theta, don't worry about that. I did mention that last time, but let's leave that for a minute, okay? And so the lower bound is the other side of the coin. So we're saying, okay, we want to find a line that's always at the bottom, like Like that is always beneath the green line, that it never goes up. Okay, it never. Now this actually looks like, the way I drew it, this looks like it's going to cross, right? If it does, then we screw that up. They cannot cross. Okay, so we're guaranteeing that it will not cross. So maybe it's just so it doesn't look like that. Let's tweak this a little bit like that, okay? Just to not confuse you, because I don't want you to think that those will ever cross, because they're not. That's the whole point of this, is that we're guaranteeing that those lines will never touch. Okay, so that omega is the bottom. Now, what does that mean? That means that in the best case of scenarios, our algorithm will never be faster than that. Like, even in the best case scenario, like it's just not going to happen. Okay, so that's what we mean by lower bound. We're basically, we have our best case scenarios, we have our kind of, like, if you think of like our average case scenarios, but we also have our worst case scenarios, right? Our worst case scenarios should never go over the big O. So we should never go over the orange in the worst case. And in the best case scenario, we should never go over red. Okay? So that's literally what big O is. Like, this is like the non-fancy way of explaining big O. Now I'm going to do the fancy way. I'm going to put a lot of math, and you're all going to be confused and freaking out unless you're math majors, which is okay. But ultimately, when I'm doing that, I want you to think back to this visual representation of this, okay? We want it to have up and down. And by the way, here's something that I wish somebody would ask, but maybe you want to ask it, but you're not here, or you just don't want to interrupt. I don't know. My question is, okay, here's what I would ask if I was sitting here listening to me talk. I would ask, well, hey, like, if we're trying to figure out a line that guarantees that it's never going to touch, why don't I just do like some super steep line like that? Because like that guarantees that it's never going to touch. Like, I mean, heck, make it like exponential. Like make something like make the following formula as your graph. Like, what, f of x, or in this case we'll call it g of x. G of x is equal to like 100x, the power of x. Okay, that is like ridiculous. Plus maybe like an intercept of like 100 too. Okay, so like that is gonna go super, super, super high. Okay, so like that's just gonna like think about it. When x is equal to 1, this is going to be 200, right? When x is equal to 2, that's 100 squared. That's massive already. Like, it's just going to super grow, like super, super fast, right? So you might ask, well, if I just want to guarantee, like, I'm taking a test, right? I don't have time to figure out what the closest line is without touching it. Let me just put that in. That's technically a big O. That is a very valid big O representation of something. Okay? Similarly for the omega, you could totally say something like, well, okay, if I really, really don't want to have that line touch, what could be my formula? What could I make my g of x equal to? I will leave that one to you guys. 0. Yeah, you could totally leave it to 0. And that is literally just like a flat line, basically, right? That's literally on the axis. In fact, if I don't want to touch 0, maybe I'll do like 0.1, just so it doesn't like look weird, right? So like maybe like there, so I don't overlap them. But yeah, you could literally just do that, and you'd be like, well, I'm good to go. My job is done here. Bye-bye, right? Well, you wouldn't be wrong. Don't get me wrong, but you wouldn't be wrong. However, let me tell you an example on where that's really not going to cut it. The whole reason we're doing this is because we're trying to, again, show off that our algorithm is better, right? We're trying to, if Jane and Joe are both trying to sell me their algorithm, Jane's going to probably show me this picture. Joe's going to show me this picture, right? Jane's going to be like, yo, look at this, man. Like, if you have a thing, like if you have only up to 100 things of data, my algorithm is fast. And Joe's like, yeah, but when you get 1,000, my algorithm is faster. In fact, anything over 200, mine is faster, right? So Jen and Joe are both trying to sell me their algorithm for my company, right? So ultimately, what they are going to show me mathematically to prove it, well, obviously, if it's a real sale, they're just going to show you cool pictures and fool you. But let's just say that we're actually fancy and trying to figure out what truly is better. Like we tell the engineers, like, yo, can you help us out and like tell us like what's actually true from the marketing? What they're going to do is they're going to look at big O and omega. And obviously more importantly for an algorithm is going to be big O. Because think about it. What we're saying with big O is that the orange line, that 1/2 x squared in this scenario, that is the guarantee that you will never go above that which means that as long as that's a good enough number for what you're trying to do, then you're good to go, right? So, you know, if you're panicking like, okay, is this algorithm going to finish on time? You look at the big O. The big O tells you the upper bound. So as long as what you're expecting is beneath that, what the big O would be. So like, let's say I'm like, okay, you know, this is like this dot right here. This is like where I lose my business. It has to finish before that dot. So if you're like, oh, okay, well, looking at the big O, we know that line is beneath it. That's guaranteeing me that I'll be good to go. That's good, right? So what I'm trying to get to here is that you always want your big O to be as low as possible without touching the green line, because you're selling yourself short. It's like, imagine this. This is the example that I tend to give, okay, for big O. Let's say that you're trying to sell a car, okay, and somebody asks you what the 0 to 60 is for that car, okay? So Tesla, they got the Tesla Plaid edition or whatever, that goes to 0 to 60 in 2 seconds, right? Or 1.99 seconds, okay? So if I ask you what the upper bound for that is, you can say 2 seconds, and I'm gonna be like, wow, that's a really fast car. You could also say 3 seconds, right? That's technically as valid as well. That line is slightly bigger. And you're still covering yourself for a lawsuit in case you don't reach that speed, right? However, why would you want to say 3 seconds when you can say 2 seconds and still be above that line? You're selling yourself short, right? So you always want to go as close as you can to that line without touching it, because it'll make you sound better, okay? Omega is not as big of a deal because again, omega is more of like the bottom, the lower bound. But you still want to keep it as close to the line as possible so that you're more realistic about that, okay? So really, big O and big omega's idea is to describe an algorithm, and you want to keep them as close as possible, which is why you go through all these things like recurrence relations and all the math that you figure out to try to make them as tight as possible. You want that boundary to be as tight. You want this space right here to be as tight as possible, okay? You want this to be as small as possible. I mean, heck, in the ideal world, you could just figure out the formula for the green line, but that is not easy to do, and there might not even exist an actual consistent line, because it might change depending on the data that you feed it. Because that's the other thing. I'm just talking about number of data, but there might be some data that really screws things up and some data that's really nice. For example, if you're doing a sorting algorithm and you give it a list that's almost sorted, some algorithms will perform that sorting really fast if they're a stable sort. Other ones may take the same amount of time regardless if the data is almost sorted. In fact, there might be scenarios where they take even slower. Let's think about bubble sort for a minute. If bubble sort, you feed it a sorted data, then it will literally just iterate one time through, see that there's no updates, as long as you have that as part of the code, that there's no change in that iteration, and say it's done. Whereas if you feed it to quicksort, which is in theory much, much faster than bubble sort, then that will tell you that like it's going to take a lot longer. And where would you see that? That's actually a case where you would see it in the omega. The omega of bubble sort is O of n, whereas the omega of quicksort is actually n log n. N log n is n times logarithm of n, which is a much bigger number than just linear time. So that's a use of omega, okay? But we'll get to that when we talk about sorting. So ultimately, the idea is you want to sell yourself with the best possible big O to show off that your algorithm is indeed better than other ones, that your car is indeed going to go 0 to 60 in under 2 seconds, right? So that's why you do that. Okay? Any questions so far, or are we good to go? This is kind of important, so that's why I decided that I wanted to refresh your mind so that when we start doing the math, you don't get confused. Cool. All right, great. So now let me pull up the math. So now what I've told you, is good enough in terms of like, okay, if I ask you what big O and big omega is, you know it. You tell me what I told you and you understand it, right? However, let me give you the mathematical representation of these things. So this is what you would see. So I want to draw this. Maybe I have it here already. I don't want to have to. Yeah, okay, I have it here. So I'm just going to copy and paste it from last semester's notes, because otherwise I spend like 10 minutes just writing something. Okay, so let me grab this. Copy. And then zoom out here for a minute. Makes it easier to paste. and then paste. Okay? Please let me know if something's not legible. So, why did I just paste here? Okay? Spooky stuff when you start seeing symbols instead of letters, right? Okay, so f of x is equal to O of g of x as x goes to infinity. That's what this means. So let me read this to you so you understand it. F of x is a formula, right? We've been using that already, f of x and g of x, right? So what we're saying is that this formula f of x is going to be the big O of the formula g of x as x goes towards infinity, okay? The arrow going like that means going towards something. So infinity is that little thing, okay? I mean, you all taking calculus, right? So I think that's a requirement for the class. So in theory, you all should be good at this stuff. But in practice, you probably all forgot it. So that's why I'm clarifying, okay? So this is what the formula is for big O. This is the real definition of big O. This right here. This is it right here, okay? That is it. That's like if somebody asks you, you want to show off, that's what you give them. Not that you show off, but if you're trying to actually do this, the real math and science, okay? So let me go ahead and read that to you so you know how to read that, okay? So f of n is equal to O of g of n. F of n is equal to O of g of n, or big O of g of n you can also read, as n goes to infinity when f of n is less than or equal to m times g of n for all n greater than n0, okay? So the little upside down a stands for all. Oops, I went back a little too many times. So I'll read that again. This is number one highlighted. F of n is equal to big O of g of n as n goes to infinity when f of n is less than or equal to m times g of n for all n greater than n0. Now n0 is going to be a number that you define, okay? So let me go ahead and tell you how this connects to what I showed earlier, okay? So let me take this graph and just paste it really tiny somewhere here so that we can see it, okay? There we go. So let's talk about this part here. For all n is greater than or equal to n0, okay? As you can see, when I was doing the Jane and Joe example, it matters where you are on the graph to figure out which algorithm is better, right? If all you care about is like this section of the algorithm, then it's clearly obvious that Jane's algorithm is superior. However, if you care about like some other section of the graph, like let's say you care about starting from a given value all the way to potentially infinity, if that's what you care about, then the picture changes, right? Joe's is better at this point. So that's where your n0 comes from. Your n0 is going to be the point where you start caring. So in this case, if my n0 is going to be 100, then you say, okay, well, I need to find a formula where this applies for anything beyond that point, okay? Or if you say your n0 is equal to here, then you need to find a formula for anything that applies after that. Now, why is that useful? That's useful to avoid weird scenarios where like the y-intercept is not 0, and also to avoid things like this where one algorithm is better in some scenarios where you're looking at really small numbers, right? Or really small n value, okay? So that's where the n greater than n0 is. So what you're trying to do is you're trying to find this formula, mg of n, that has to be, you're trying to find this f of n formula, apologies, that's less than or equal to this formula, okay? So to give you an example, this f of n is actually your real graph. So this is the squiggly line, okay? I might have mixed up my definition, so I want to make sure I don't confuse you with all this stuff. Let me get this picture in there because this will help us out a lot. This is where I wish I had like an actual real board. One of the few times, because I actually don't like writing on the board too much. But here, yes, because otherwise I have to make things tiny and like manipulate stuff, okay? So, looking at this graph, the green line is going to be f of n. Right now we're not looking at anything with the red line, so I'm just going to try to delete it. At least I'll delete this much. Okay? And then I think I can just select that. There we go. Okay? So we're looking at big O, so we're looking at that. So the green line is going to be your f of n. Okay? And then on the other hand, what we're trying to find is this. So that is going to be the yellow line. In fact, maybe I should use the yellow for that so you don't get confused. So that's yellow, and that's your purple. Okay? So we're trying to find that formula that is above it. Okay? And that formula is made up of two things. It's made up of this m constant, and it's made up of an actual function. Okay? And then we're saying for all n is greater than n0, this will be true. Which in this case, you know, it's pretty much the case since the beginning of the graph, right there. But in the case of that one over here, then you would have to pick that n, you know, assuming that you that you have a line like this. This is the line that you're working with. This is going to be your what is it, g of n? Yeah, your g of n. So that's going to be your g of n times m. Okay. If that's the case, then your n0 is going to have to be wherever that goes over it. So like right here. Okay? Assuming you're working with James' line. So are we all on the same page there? And by the way, I don't know why they chose omega. I think it's because it's the bottom of the, like, I think it's the last letter of the alphabet, so like lower bound, but I have no clue. I was pointing at omega. I'm not sure what you mean by that. Oh, yeah, sorry. Ooh, good point. Good call on that. Thank you. So, yeah. Big oops there. This should all be pointing at this one. Okay, there we go. Thank you. Thank you for calling me out. Yeah. My bad. That's what happens when you copy paste, right? So, anyways, yeah. So, think about the way that this is saying why this is less than. Right? It's less than because you always want to keep the line beneath it, right? So you want to keep the green line beneath the yellow line, right? In fact, maybe because that's green, I should make this green, and I should make that green here, so we don't get all the colors mixed up. Yeah, this looks more clean now. Okay? So yeah, so we want to keep the green line beneath the orange line. And so that is why it has to say less than, because you want to guarantee that. And so what's this m value going to be? What this m value is saying is that, you know, when you figure out whether something is quadratic, linear, logarithmic, whatever it is, if you're just trying to kind of make it a little bit steeper or a little bit less, but it's within that same asymptotic complexity, m is going to be some numerical constant that you can throw in to get around that, okay? So like, what I mean by that is if you have a graph that is like this, and you're trying to make the orange line be above that, you know, you could totally pick a line like this, right? Because it might turn out that this line is actually something like, you know, your f of n is going to be equal to, I don't know, let's just say this is 2x squared, okay? But we don't know that. Maybe let's just say for the sake of this, like we don't know what that is, but let's just say it's 2.1x squared, okay? So then you just pick this to be 3x squared to kind of be okay, right? And so these values are constants, and it turns out that when we're comparing algorithms, constants don't really matter. Like what we really care about is this part, the x squared part. And so we actually dropped in when we're talking about asymptotic complexity. So when I say this algorithm, like I was saying earlier, when I was talking about quicksort, lower bound being n log n, there might be a constant associated to that, like 3n log n, or with bubble sort, there might be a constant, although that one there isn't, but at least with other ones there might be. It turns out that the constant is not something we care about too much. Now, I know what you're saying. You're like, well, wait a second, you know, like we're trying to sell ourselves the best way possible, right? So we want to put the best numbers there. Yeah, true. And maybe in those scenarios, it might actually matter. But in the general overview of algorithm analysis, we don't really care about that. We find that to be insignificant, even though the difference between a 1 and a 2 as a constant is literally twice the time of something taking. But we're saying that's irrelevant considering some of the growth rates that we might see. Okay? So not to disregard it. We're still going to show you examples where that m is like that. But I'm just telling you in the real world, it gets dropped a lot, okay? So that's big O for you. And it turns out that big omega is the same thing, with the only difference being that this sign is flipped, okay? Because now, if I take the same graph but delete the other parts now, so let me take the same graph again. Shrink the graph. Oh, I don't like the fact that it got crooked. There we go. Okay. So let's go ahead this time and delete the other side. So let's delete all this stuff. There we go. Get rid of the theta so you don't get confused. And yeah, so this time, this is our f of n. And then the red one, so this red, is going to be our g of n, right? And so there's that g of n, and there's that f of n, okay? And again, we want to keep it greater, so we want to keep f of n bigger than g of n. And again, in this case, what that constant is probably going to end up being could be less than 1. It could be like 1/2, right? So let me give you an example of that scenario. So here we got, oh, sorry, not what I meant to do. Here we got the same formula as before. So this is y, or sorry, not y. F of n is equal to 2.1x squared. And in this case, actually, we can just make the that bottom line be g of n is equal to 2x squared. Although technically, what we would say is that, and then put the 2 there, right? So because really m is equal to 2, right? But anyways, just so you don't get confused, think of it as 2x squared. But again, you drop the 2. Doesn't matter too much, okay? So, yeah. Okay, hopefully the throwing you the math didn't throw you off. But again, you know, if I started out by showing you this before I talked about all the other stuff before it, I think you all would be a little bit more confused. But please let me know if I should have just gone straight to this, because then we would have saved like an hour or so. You know. Finally, let's talk about theta. I'm actually really happy I can copy and paste this. So that's, I guess, that's a plus for the tablet, because I can just copy and paste this, which means not spend a long time writing it. So, okay. Oh, look, it's a pretty omega symbol. This is what omega should look like, by the way. That's like, you know, expectation versus like reality, right? Like, Mom, can we have omega at home? We have omega at home. And then omega at home is like that. Whereas this is like the pretty omega, right? Okay, so yeah, you will see that sometimes it's difficult to draw these symbols. So, you know, I sympathize. So, okay, but anyways, theta. So theta is weird, and we don't necessarily talk a lot about it in class, but it's like an in between. Okay, so it's like you want omega, you want big O, and you want them both together. So what do you get? You sandwich them all together, and you get theta, right? So as you'll see that the formula is a combination of both formulas, essentially. So we have the formula saying f of n is equal to theta of g of n when, let me highlight it as I go, since I'm actually you'll follow along. So we start out by saying f of n is equal to theta of g of n when f of n is equal to big O of g of n and f of n is equal to omega of g of n. And then, I guess I should put an and here, and g of n times a constant k1 is less than or equal to f of n, which is less than or equal to g of n times a constant k2, okay? So what does this all mean now? What this means is that we are trying to actually find, we're trying to squeeze this as tight as possible, and we're trying to sort of to find that that in between. Now, this is dangerous, and people always think of this as average. Theta is your average, but it's not. It's special and weird. And when you take CS 477, they're going to go more into detail with theta. But it is definitely it's not no it's a little bit of everything. Okay. Like in reality though, let me tell it to you in real world terms. In real world terms, you're going to use theta when you actually can figure out what the green line is. Okay. Yeah, it's kind of like an acceptable range, but like in practice you use it when you can actually figure out what the line's formula is. So like if you can actually figure out, because I mean, you know, I'm giving you the example that sometimes it's a squiggly line, but sometimes it's actually going to be a line that you can actually figure out the exact formula for, and it's not like some super nasty formula. That's usually when you use theta. So when we're doing actually the recurrence relation stuff, we're actually going to be using theta. But other than that, you won't see it in the class. Other than sometimes like as a reference, like, oh, by the way, the theta of this is this. But most of the time it'll be in the middle of both of them, okay? So like the most common scenario as well. So like when you see something like quicksort's upper bound is n log n. The bottom bound, lower bound is n log n. Guess what? The theta is literally n log n because it's like in between both, right? So whereas like something like bubble sort's lower bound is n and the upper bound is n squared. Turns out that the theta is pretty much touching n squared because other than that special scenario where like it's a sorted list, bubble sort sucks. So it's not a shock that the theta is n squared, okay? So it's like the range that is most likely going to happen. But I don't want to say things like median, min, max, mode, or average because they don't tell you the whole picture, right? So if you ever ask, don't say that. Don't say, oh, theta is just the average, because like, oh, yeah. Say it with like little quotation marks, like asterisk, like, you know, like terms and conditions below or something. Okay. So and the way, yeah, it's kind of like closer to, yeah. So the way you do that is you basically just combine them. So if you look at this, we have over here, this right here is going to be, here, let me drag it down so y'all can see it. I'll copy. So this is from big omega. So we're copying big omega down here. So this is the big omega stuff. And if we flip the sign, just so you can see it, so, you know, okay, this is kind of weird, but we're going to flip it upside down just so you can see it. Okay, so you can see that this, you know, other than the fact that it's upside down, we can flip this up now. We can flip this up now. That, except for the sign now being all weird, this thing, but other than that, that is literally this, right? Here, that's literally that right there. Except instead of using a K, an M, we decided to use a K. And we subscripted, okay? So you can see that that right there is the same thing as this. So that is your omega, okay? I can do the same thing with the other side, with the big O. So literally, it's like you just combine both definitions and you get theta out of that, okay? This one I don't need to move. It's like, you can see that it's the same. So like this right there is the same thing as this right here. Again, instead of using the variable m, we just decided to swap that just because we can to a k, but we say k1 and k2, okay? Because like, you know, it's like imagine you're naming your variables in a program, you know, you say like k1, k2 as part of like some variable array. You know, actually, I hope you don't actually do this. Like, if you're declaring two variables, you know, you don't do that, right? You hopefully make a tiny array or something. But I guess if you have two pieces, maybe. But like 3 or more, I would make an array, right? But yeah, that's why they just changed it from n to k. Okay? So this is no magic. This is literally just both things combined. Okay? And that's again the mathematical representation of that. Okay? That's it. That's theta right there. So yeah. That's it. That's your big O. That's asymptotic complexity. For the rest of the class, what we're going to do is every time we talk about an algorithm, we are going to say, okay, I'm going to show you what the algorithm is. You know, we'll explain it, draw some pictures, talk about it. But then I'm also going to tell you what the asymptotic complexity of is. So then you'll know. Okay? So let's talk about a couple of the different asymptotic complexities that you can see. Well, we already said two of the popular ones, right? We said O of n and we said O of n squared, right? This is called linear time, and it's very desirable because it's a linear growth. So if we have 100 things, then we have 100 operations. If we have 1,000 things, then we have 1,000 operations. It can be, frankly, if you can find an algorithm that can do something in linear time, you are pretty well off, okay? However, there's better than linear time, actually. So maybe I should have started this list a little lower. There is logarithmic time, okay? That one is written like this. And again, we talked about omega, we talked about theta, and we talked about big O. But as you can see, what we tend to care about is worst case scenarios or upper bounds, right? So we typically worry more about the big O and not really think about the omega. The omega we only think about for like those special best case scenarios, like again, if this list is sorted already kind of thing. So you will see me focus particularly talking about big O and then just briefly mention omega, but at least you know what it is, right? Because like again, if you're trying to figure something out, like that's great that things finish fast in the ideal scenarios, but really what I want to know is like, okay, if what's the good news and bad news kind of thing, right? I want to know the bad news. I want to know what the worst case scenario is. I want to know what the realistic thing is going to do, right? So I care more about that big O because I want to be prepared. So that like if I have a customer in my business and I hit that big O in terms of time, I want to know how slow that's going to get for him, right? It's like people do it in the app, right? And we're trying to calculate how long it takes for the OCR to scan the nameplate and give you the arrows for the map, right? Like I want to know what the worst case scenario is, and I want to make that be as like acceptable, right? I don't care if in the best case scenario, like things get done in half a second. I want to know what the worst case is. So that's why we talk about big O and focus on that, okay? So anyways, talking again about big O, we have logarithmic time. Logarithmic time is really nice because like your data can grow, but the operation count grows even slower than that, okay? So logarithmic is going to be a much flatter thing than linear. So that's actually really nice, okay? You will see some algorithms this semester that are logarithmic in nature, such as when we are inserting into an ABL tree, or in general when we're inserting into any balanced tree. That will be logarithmic. But other than that, you won't see that too much. From here, there is actually something in between linear and quadratic that is popular. So typically, when we're doing these things, the next thing here is like O(n) cubed. I don't know how you call that. Not cube, but tertiary time. There's like a proper English term for n cubed time that's not quadratic. Tertiary time or tertiary, something like that. Google it and then tell me if anybody can. But then you go to N4 and so on, right? And then finally you get to the things that are ternary. Is that it? I mean, I'll trust you. I don't know. So if it's ternary, then let's go with ternary. I don't think it's ternary. I don't know. Maybe. No, because it sounds like secondary, ternary. I don't think it's that. Is it? Tertiary. That sounds better. Tertiary sounds right. Thank you. Cubic. Cubic also sounds right, by the way. Okay. Quartic. Quartic sounds right, too, for that one. Okay, so we'll do it with either or. Again, I don't ever make you write these things. What I make you write is the numbers. Because A, it's faster to read this than this. Less writing, too. And also, who writes numbers and letters, right? Cubic, quartic. Okay, so you think it's cubic? All right, we'll go with the cubic then. Thank you for checking. Appreciate it. So, okay. So, yeah. But again, it's good to know what these things are like. But I mean, other than linear, we tend to just like say things with the numbers themselves, So that's why like, I don't know them off the top of my head. Plus, numbers are borderless, right? So you talk to me in Spanish, you talk to me in English, but you could also talk to me in numbers, and I would understand, right? So numbers is better. Okay, Wikipedia, yeah. Okay. So, anyways, from here, eventually you get to one that I actually do know the name of, which is exponential. And that's when you start to see things like a base number that is fixed, and then the exponent is where your n is or your x, So like you get that one, and so on. Okay, but some power. like that. Because if you don't believe me, just try to draw the graph. But like these things are just going to grow insanely fast. I mean, I gave you the example earlier, right? I mean, let's even look with powers of 2, right? You get 2, 4, 8, 16, 32, 64, 128, 256, and 512, 1024, 2000. You get 4000, 6, and then 8000. So in like 20 numbers, you're already in the over thousands range, right? So with any exponential one, you can't get there. And again, we're looking at sort of the long term of these things. Initially, again, some of these might grow slower than the other ones, right? But in the long term, like, because I mean, let's say for example that you're trying to compare something like x squared, and actually let's do something. Okay, let's do x squared plus 200, and you're trying to compare 2 to the x. Okay, something like that. Initially, this will grow faster, but at the long term, I mean, this thing's gonna beat it like way fast, right? So like what this graph would look like is something like that, whereas this one is literally gonna go like that. Okay, so this would be your n0, by the way, when you're comparing things. So yeah, okay. Exponential doesn't seem like wherever we want to be for quick operations. Yeah, absolutely not. If you have an algorithm that takes exponential time, you have a real problem. In fact, maybe at the end of the semester, we shall talk about NP, sorry, P versus NP, and like deterministic versus non-deterministic functions and things like that. And if not, then you will definitely talk about them in automata and the algorithm analysis class. And so it turns out that most of the algorithms that we do in this class, in fact, all of them, I think, are polynomial time. Polynomial time is anything that has an exponent there. That's polynomial time. This set of algorithms is exponential time. There are certain algorithms and mathematical problems in computer science that we don't have an algorithm that can achieve it in polynomial time. Even if it was like n to the 1000, but it was always n to the 1000. We can't. There are some things like this, such as a knapsack problem, that can only be solved in exponential time. Nope, encryption and decryption. Actually, well, yes and no. So in encryption and decryption, there are certain parts of encryption and decryption, like the factorization, that don't have a solution in polynomial time, but it's kind of a special case. So I would avoid that specific example. Okay, so factorization of primes. See, that's a special case. I think factorization of primes was thought to be exponential, but then like they weren't sure. So then it got solved like some years ago, I think. I can't remember. There was something with factorizations that was solved. And they were like, oh yeah, we can do this in polynomial time. So that one's like a special case. I'd have to check on that. I don't remember off the top of my head. I just know that something was discovered about that. So Google that one. But anyways, yeah, I might be thinking of something else, but yeah, check it to be safe. Anyway, but yeah, so knapsack problem, all these are so rusty because I wasn't thinking about talking to them today. But there's the one with booleans that you have to figure out. The SAT problem, yeah, the satisfiability problem is the original, the OG, like NP problem, and then there's NP hard and NP complete. And so these are problems that we don't have algorithms for polynomial time. And so we have algorithms that can solve it in exponential time, which is horrible. And so the real question is, is it because we haven't found a solution, or is it because there is no solution that can do it that fast? And that's the whole P versus NP. So that's all I'll say about that, because again, I could go about this for hours, and they will talk about it in other classes, but just look up P versus NP, and then figure out. We don't know, by the way, the solution to this. Majority of people think that there is no, it's not that we haven't found it yet, it's just that it doesn't exist, but it's not proven. So that's why there's a big question. And there's like $1 million rewards if you can prove this. So if you want money and you can actually prove this. Actually, forget the money. If you prove this, like, you're going down in history. So yeah, but who knows what will happen. So yeah, and I have a video on the 302 playlist from spring 2020 that I talk about this stuff. So you can always check that out if you're curious too, if we don't get to it this semester. But I try to do it if we have spare time, but sometimes we do, sometimes we don't. Okay? Yeah, I don't know what movie you're talking about though. No, it's not that bad, but it will definitely screw up with a lot of secure things because, you know, we kind of expect things to be slow to solve, and then, but it wouldn't like destroy society. It would just be a little bit of hecticness and chaos and whatnot. It actually would be good for society long term if things were not, if we can make it, you know, we can speed up a lot of things. So the initial thing would suck, but long term would be good. But I don't think they're equal. So anyways, that's exponential time. But we care more about polynomial in this class than quadratic, cubic, quartic, linear. But even then, like, frankly, if we're looking at algorithms, I would say that this is a good line where anything beneath that is something that I really wouldn't want to use for actual, like, usable stuff, because it's already pretty slow. In fact, really, I would have more, see, actually I can use yellow as a warning. So this is more like, okay, this is kind of already not that good. And then, of course, anything above that is nice, right? N-cubed stuff we'll see. Some of the graphing algorithms are N-cubed, but the majority of things we'll see are N-squared or less. And it turns out that there is another one in here. There is N log N, which is linear logarithmic time, I guess. And ultimately, what that one is not really its own category, but it has become, just because it's such an important thing. It turns out that the best sorting algorithm that we can come up with is n log n. That's going to be your big O, the best big O. We can't go anything lower than that. There's no sorting algorithm that can finish in n time that is using comparison-based sorting. Okay? And what this is a multiplication of that. So it's kind of like combining these two and multiplying them together. So I'm putting that as its own sort of category because it's so popular, but you don't really classify it officially, but it's very popular, especially with the sorting stuff. And a lot of other algorithms, you'll see it a lot listed, okay? So, yep, that is going to be your different naming stuff. Oh, fun. Now we get to do some code. Okay, so there's two things that I want to do now. We have 8 minutes, so let me just, well, let me tell you what's going to happen in the long term. First, I'm going to show you some logarithmic rules next class. So refresh your logarithms, you know, like how to convert logs and things like that. But I will show you them. I'll show them to you as well. So we'll do that next class. And the thing that we're going to do, and I'm going to do it right now, is we're going to start looking at code and trying to figure out what the asymptotic complexity of code is. And so let's start with a simple example of that. Okay? And I believe I have an assignment on this as well. I don't know what I have it do, but I will modify that. Inside equals 0, I. So here's one of the few times you'll see me code in class. I is less than n plus plus. And it really doesn't matter what's in the loop, but let's just say stuff. Okay. Or here, let's make it more useful. Let's just see count is equal to 0, and then we're gonna make plus equal I. Okay, so now stuff is happening. But of course now we need to add curly braces, right? I saw someone, I don't know, I remember, I think it was 202, but they wrote an if statement, and they put a semicolon there, and then they put a return afterwards, and they were confused why the code was broken. And then I saw that, and I was like, not good. But it sucks because I responded like 4 hours later. That was when I was busy on Saturday. So for 4 hours, they were probably like freaking out, right? But yeah, okay. But anyways, that's a warning for you. Don't forget, don't put semicolons after your if statements because you'll kill it. So yeah, okay. So here you got a piece of code. And if I ask you, what is the asymptotic complexity of this code? What is it? Well, this is the first one you see, but yes, you are indeed correct. Well done. This is indeed linear time O of n. Very good. Now, how did you come up with this solution? Well, it turns out that what you did, hopefully, is you looked at the for loop, right? So you looked at the for loop and said, how many times does this run? How many operations is this loop going to go through? Well, it starts out at 0, as we can see here. I don't like yellow for that. And then it goes all the way to basically n, right? Well, I is less than n. So let's say that n was equal to 100. So this loop is going to go from 0 all the way to 99, and then the next time it goes around with 100, it'll jump out of the loop, right? Because this will no longer, the I is less than n statement will no longer be held to true. Great. Well, there you go. That's it. That's all you got to know. I mean, like, now you are able to analyze asymptotic complexity of any code, right? Cool. Except not all code is as simple, of course, right? So let's look at other examples of code that may not be this particularly trivial. But this is something I would like you to do. Revisit some of your assignments from other classes, or even for assignment number 1. And take a look at the code and try to see, like, what is the asymptotic complexity of this code, right? So let us do another example. We'll just keep doing examples until we hit 15. So probably this will be the last one. But yeah, we'll start class next time with more examples. Let's do another one. Is that gonna compile? That should compile. Yeah, okay. All right. Do we have any guesses for this one? Quadratic. Yeah, very good. N squared, indeed. How did you all come up with that? Well, remember, this inner loop is going to be running basically the entire n. So this is literally going to be running for n time. And then this one's going to be running for n time. So basically you multiply both n times n. And that is indeed how you get quadratic. Like that. Sorry, that looks nasty. There we go. Okay? Very cool. That actually took 1 minute, so let's just do one more. Yeah. Let's put the curly braces on that one. But yeah. How about this one? Two n. Very good. Yes, you are indeed correct. In this case, these are not nested, so we have this basically n plus n. So whenever something's not nested, you don't multiply, you add it. So indeed, this becomes 2 of n, and really, ultimately, you kind of drop the 2 of n and you just leave it as n. But this is perfectly valid. In fact, this would be like your theta, if anything. Okay? So, yeah, that's an example of that. So now you've seen, when things are nested, you multiply them. When things are sequential, you add them together. And that is pretty much how this works. Of course, next time we'll do some other fancy things in the loop that will get confusing. Then, of course, we all remember recursion from 202, right? Well, that can be very interesting to also figure out the asymptotic complexity of. So, yep, that's all in our future for Wednesday. But I think that we have enough for today. So, any last minute questions before I stop the recording? I hope that you all learned a lot today, because this stuff is like the fundamentals of the course that we will need for the rest of the course. So, because like now, for all of your assignments, when you're doing those write-ups, this is literally what you're going to be doing. You're going to be analyzing your own code that you wrote, and you're going to be telling me what the asymptotic complexity of that code is by doing these basically, you know, conversions of like code to actual asymptotic complexity. And so, I mean, hopefully the fact that you wrote the code means that it's easy for you to read, right? But I hope that's the case. But because you're going to have to be basically trying to figure out what the asymptotic complexity of your nasty code is, if it's nasty or beautiful code, right? So don't worry though, that gives you more than enough things to write about for your for the paper for the write-ups, and that is going to be ultimately something that is good, because by the end of the semester you will have plenty of write-ups where you practice this, what I'm doing right now, so you become good at it, and then in the future when you see somebody else's code, you're gonna be like, oh, well, this is n squared. Okay, cool, not bad. Or, oh, this is exponential. Like, ooh, no. Fix this code or like do something else. Oh, by the way, the last thing I'll say about the exponential stuff is that not all hope is lost for this stuff here. There's heuristics to the rescue. Heuristics is educated guessing. And there are certain type of algorithms that basically guess what the solution is. And while they're not 100% of the time correct, they are a lot of the times correct. And that's a sort of a nice workaround to solving some of the exponential problems. So, you know, I don't want you to go home and like tell people like, oh, exponentials suck and there's like no way to solve them quickly. Yes, technically there's no way to solve all solutions quickly, but with heuristics, you can solve things rather quickly and they will be right enough times that you're okay. But whereas something that is polynomial, you're guaranteed to get all the answers all the time correctly under the time. With heuristics, because it's a guess, there's always a chance that it might be wrong. So, yeah, I thought I'd say that. Okay, correct enough. Yeah, that's a good thing. I like that. That's a good way of saying it. But yeah, that's it. Already in my other class, there are people waiting. Again, next Wednesday. Not the next class will be on WebEx, but the class after that, we have Labor Day, and then Wednesday that will be on Twitch. Great. Thank you all for coming. I hope you learned a lot today. And yeah, make sure you send me or the TA any questions you might have as well. Like I said, I have a class right immediately after this, so I might not respond, but I'll get back to you soon. And for those on YouTube, thanks for watching. Don't forget to like, comment, and subscribe, I guess. Let me stop the recording.